So, see, as you can understand that in the last few weeks, we were in the last few weeks we were talking about different types of optical sources, lasers, etc. So, the usefulness is, of course, we all know biophotonics involves optical sources, lasers, and for certain measurements, sensing, monitoring purpose, diagnostic purpose, etc. Okay. Even therapeutic applications, right, for surgery, in surgery also it is used. So, just to give you an idea that when we work with biophotonics and when we work with the tissues, etc., what are the constituents, right, which are interacting with the optical sources, and that will give us the indication that what type of light source or the wavelength range, etc., we can use for certain applications. Okay. So, I have given this, of course, this picture is very clear, but x axis is the wavelength, okay, and y axis is the absorption coefficient, or basically it represents the extinction of light when it interacts with this type of particular constituent. For example, if you see a very blue color line, which is water absorption with different wavelengths, and you can see that there are certain wavelengths where the absorption is quite large, and the one is around UV region 193 nanometer, okay, or 249 nanometer, krypton fluoride laser, argon fluoride lasers, they are all pulsed lasers, okay, pulsed lasers. I have already told you the lifetime, upper state lifetime is only few nanoseconds. So, it is automatically it is a pulsed laser. So, you excite with electrical discharge and observe the lasing operation, and at with argon fluoride or krypton fluoride, etc. As well as there is another band here which also experiences very large absorption, right, by water molecules, and that is erbium YAG laser. So, this is this lasers, and of course, there is one more wavelength 10.6 micrometer all the way, right, this is in nanometers and this is in micrometers. So, it is very long wavelength comparatively. So, 10.6 micrometer wavelength CO2 laser. These are the lasers which are predominantly useful for surgery or therapeutic applications, removing material or ablating the material, or drilling bone, or or teeth, or for cosmetic treatment, or for certain heating process, okay, in ophthalmology, etc. In surgery, we also use, in order to interact light interaction with cornea, during cataract surgery, etc., during for correcting the lens of the eye in the eyeball, etc., we use argon fluoride, krypton fluoride lasers, etc. Okay. Recently, we are also using femtosecond pulsed laser, a titanium sapphire laser. Okay. So, these are the lasers. So, titanium sapphire laser central wavelength is around 800 nanometer. So, of course, the absorption by water is very less, but some of the lens material, etc., the absorption is to certain extent it is available, which is used. Okay. Through multi photon absorption, the whole process is controlled in femtosecond laser. When we come across therapeutic applications, we will try to see those aspects, very specific such things, but in general these are the lasers. Secondly, for diagnostic windows, okay, for sensing, etc., we do not want laser to interact with the tissue to generate heat or ablate the material. What we want is it should just interact with the material, excite the material, so as to provide us some information related to scattering, absorption, right, or some polarization change, etc. If we can capture that information, it is good enough to, right. So, this window is such that the absorption by most of the molecules should be as low as possible, as less as possible. At the same time, specific absorption may be important, right. When we talk about pulse oximetry, I will use 660 nanometer and 940 nanometer, let us say, line. Now, why shall we use that particular, those particular wavelengths? Because absorption of oxyhemoglobin, hemoglobin molecules, etc., is taken care through that. Okay. So, absorption is useful, but distinct absorption to distinguish various such constituents is also, right, important, and that window is in the visible range. Okay. So, you can see that wavelengths are ranging from, if you see this window, the wavelength ranges from 400 or plus 400 plus nanometer to 1000 plus nanometer. Of course, beyond 750 800 nanometer, it is near infrared, it is, we cannot see, not a visible range, but slightly, right, from visible range to near, very, right, not very far, but near infrared range, okay, up to 1060 1050, right, nanometer. Okay. So, this is the range within which we try to use lasers for sensing purpose. Of course, there is one more range around 1.7 to 2.2 micrometer also. Of course, absorption by water molecule is large. So, extinction is very fast, correct. It will not be able, light will not be able to propagate for longer distance. Why? Because by the time it propagates to capture some information, the light is getting absorbed by water molecules in the tissue. Then reflected signal, we will not be able to capture any information. Okay. So, in that sense, this particular wavelength range 1.5 2 micrometer wavelength range is little useful, but not so much for the depth, right, information, but still it is useful, and it is also useful for sensing purpose. Okay. So, slightly extended band, okay, up to 2 micrometer is also used. So, now you know that if I am applying for sensing applications, which is what is the window within which I will be generally working. Okay. Of course, I can work with different other wavelengths, but then scattering or absorption losses or interaction with the molecules, etc., may be slightly different, and it will generate heat or some other, right, aspects where signal will not be so large, and that will limit the, right, wavelength range, as you can understand. So, this is very important, and if we talk about, let us say, currently what are the lasers that are useful. In the past, a few lasers were used, but now they are not being considered, although they are useful and applicable, but because some other current laser sources or optical sources can efficiently provide the output as compared to the some of the past lasers. So, in the past, ruby laser was used. Okay. Ruby laser means chromium doped sapphire with the wavelength, right, around 694 nanometer, red color, was used full for some of the biophotonics applications, right, particularly right, particularly for some of the spectroscopic measurements, this was useful. But today, most of this laser is not being used. Today, mostly neodymium, YAG, yttrium, aluminum, garnet, okay, laser is used. What is the fundamental wavelength? 1064 nanometer. Okay. Okay, and of course, with second harmonic, this is the fundamental wavelength. Okay, and second harmonic generation will give us 532 nanometer output, which is in the visible range, okay, second harmonic generation, it is in the visible range, and the third harmonic generation is 355 nanometer, which is right in the UV range. Okay. So, this wavelength third harmonic generation etcetera, maybe 266 nanometer, fourth harmonic generation etcetera, they are used for therapeutic some other right related to bio medical applications, where you tissue interaction with the laser will end up with ablation, heating effect etcetera are used. However, major right source 1064 nanometer is useful for hair removal, tattoo, skin related issues etcetera taken care. 532 nanometer is visible range, it is useful for some of the applications related to retinal right correction, detachment corrections etcetera, because 532 nanometer light can propagate through, okay, easily, it is visible. So, it is possible to use it for retinal right correction etcetera. Absorption is less, but still it is useful. Okay. So, this wavelength. So, neodymium YAG is a very good replacement. In fact, there were other past argon ion laser, okay, gas laser. So, argon plus, sorry, argon plus ion laser, okay. Its wavelength is around means it has 488 nanometer and 514 nanometer, but nowadays, because argon ion laser efficiency, cooling if etcetera required, it is a bit right cumbersome maintenance etcetera. That is why neodymium YAG laser with 532 nanometer is useful to, it is replaced this type of lasers, okay, gas lasers or solid state ruby lasers etcetera. So, neodymium YAG. Then I told you that even erbium YAG laser, okay, has a wavelength around 2940 nanometer or 2.9 micrometer etcetera. Okay. So, this is close to the absorption line of water, as I already showed you, okay, as well as it is also being absorbed by some of the tissue materials. Okay, that is why it is useful for various applications, smoothing of skin, resurfacing of skin, it is possible, okay, smoothing, resurfacing, even it is possible to drill, remove the material also, okay, bone, teeth etcetera, for removal of the material, it is useful, okay, 2020. So, holmium YAG, which is the wavelength is around 2100 nanometer, and it is useful in, so here it is useful for skin, right, tooth, teeth, bone, it's right, either material removal or resurfacing etcetera, right, okay, material. Okay. To holmium YAG, it is for basically related to tissue ablation, okay, tissue ablation, nothing but the material removal basically, okay, kidney stone removal etcetera, kidney stone. Holmium YAG can be transmitted with the help of optical fiber, right, and it is possible to even remove the right kidney stone. Okay. Then titanium sapphire laser, okay. We know wavelength range is 650 to 1100 nanometer, central wavelength is around 800 nanometer, okay, and it can work in a tunable form, tunable laser, or as a very ultra short pulse laser, right, we talked about it, femtosecond ultra short pulse laser, because spectral width is right is wide, ultra short pulse laser, and it is a very good, very useful, right, laser for non-invasive, as a non-invasive tool, okay, non-invasive tool, but invasive tool, and heating effect is quite low. So, it can interact with tissue without damaging the tissue to the extent possible, of course. Okay, and it is underlying biological phenomena can be studied. So, biological phenomena, right, can be studied, okay, with this. However, the thing is, it is yet to be used extensively in the clinical application. Okay, it is maybe laboratory, but it is still very useful in the laboratories. Okay, very useful titanium sapphire laser. There was alexandrite laser here, alexandrite laser. So, again similar to the solid state, it is a solid state laser, alexandrite laser, which wavelength range around 700 to 830 nanometer. But because of the titanium sapphire laser, which is having a vast, right, it can be tuned broadly, etc., it has replaced this alexandrite laser. So, it is the past. Okay. Now, there is one more important laser, gas laser, which is helium neon laser, okay, where output wavelength is 632 nanometer, okay, and it is useful 632.8 precisely a nanometer, and it is useful for confocal microscopy application, okay, DNA sequencing, etc. It is a low power laser, okay, flow cytometry, it will, etc., okay, and hematology application, okay, helium neon laser, okay, and CO2 laser, gas laser. But of course, the useful, it was very useful in 1990s and 2000 for certain ophthalmology applications, etc. Still it is certainly cosmetics application, it is still useful. However, the other lasers such as neodymium YAG laser, arabium YAG laser, titanium sapphire laser are slowly, right, they are replacing this CO2 lasers, considering its right maintenance, etc. But it is quite cheap, it is not so costly, right, we can the laser system can easily be, right, used for. So, wavelength range, wavelength is 10.6 micrometer, okay, right, 10 times that of the neodymium YAG laser wavelength. Okay, 1064 nanometer means 1.064 micrometer, correct. So, 10.6 micrometer this. Okay. It is useful in surgery because of the water absorption, ophthalmology and cosmetics. Basically for therapeutic applications, right, interaction of tissue, ablation or photodynamic therapy, etc., it is useful. Need not be for sensing or diagnostics, right, applications. Okay. So, so now I hope you got in general, see whatever we learn, right, right, out of that, these are the currently used, right, optical sources, light sources. There are xenon lamps, etc., tungsten lamps, xenon lamps, they have a very broadband spectrum, but the intensity will be quite less. So, those are not the laser sources, they are optical, right, sources which can also provide a wavelength range for certain measurements, okay, particularly in blood sample analysis, etc., where you want to analyze various constituents of in the blood, right, glucose, maybe hemoglobin, maybe oxyhemoglobin, maybe some other, right, tissue aspects to be measured, then we need widely tunable. So, in that case, it is not that we need a laser source, we can use a broadband source and a filter, and then tune the filter to different wavelengths and extract the information, okay, using this. So, now yesterday onwards we also started talking about various types of sense, means what are the optical sensors in general, okay, which are useful for right for biophotonics applications in general. So, that is what we started talking about yesterday. So, it is basically optical sensors and okay. So, optical sensors are of different types. One is semiconductor based, right, sensors are possible, semiconductor based sensors. Okay, and the other one is we can use photo conducting devices, and the third one is the thermal based sensor. In infrared range, we can use this thermal, right, based sensors. Okay. Right, and semiconductor based sensors are basically photodiodes, okay, mainly photodiodes that we use, okay, photodiodes or right, avalanche photo, different types of photodiodes are available, avalanche photodiodes, etc., etc. So, we were just trying to yesterday we studied about some couple of modes of operations of this photodiodes in the non-biased mode or in a reversed bias mode. We also understood that reverse bias mode is useful, right, because in order to measure the very low input power also without much of difficulty, and in photodiodes there is also either it will be based on PN junctions or it may be based on PIN junctions. Okay. I stands for intrinsic layer, okay, in between depletion layer will be there, and right, and this allows fast response characteristics, okay, comparatively as compared to PN junction where the capacitive effect increases the time constant, and it is a rather a slow measurement, but fast response characteristics if we want in order to measure, right, as output we use PIN, right, junction. However, because of the depletion layer, very small depletion layer in between, etc. So, the basically the output power is quite less, okay, the not power, but the output you can say sensitivity, response is quite low, responsivity is quite low, response in terms of output current, etc., which is quite low, and hence may be limited to right, to certain extent in terms of measurement of low power. Okay. So, low right, it is detects you can say that low power detection is little difficult. Okay. Low optical power, of course, detection is challenging. Okay. It is little challenging, we need some other arrangements to amplify the output, etc., and here the sensitivity and the power is right, it is it can measure very low power also. So, low power measurement is possible, low power optical measurements, of course, measurement is possible, is easily it is derived up to, right, but response temporal response, right, is fast response. Temporal, when I say time dependent, right, response is quite fast in case of PIN photodiode, and in case of PN type means photodiodes, it is quite slow. Okay. And we were just talking about so in case of photodiode, let us say PIN type, etc., where intrinsic region is there, photon when they passes through, they will dissociate hole and electrons will go towards N, holes will travel towards P. However, when they are traveling through this intrinsic region, they may get diffused also. Okay. They may not reach to n region to transmit the current, okay, that is also possible, and it depends upon the diffusion coefficient of this electron when mobility basically is right is important. Secondly, the amount of light which is, let us say, photon energy h nu interacts, and the amount of light which is getting absorbed when the light is propagating through this material. Okay. So, these two factors they determine indirectly if my intrinsic region is very large long enough, then there is a possibility that the electrons, if it is wide enough, the electrons generated may not be able to reach n, but then the number of photons which will interact with this region will, if it is wide, number of photons which will interact will also be large, but if it is less, very small region, number of photons interactions will be less also. However, if you consider the absorption by this material, then diffusion will, not diffusion, but the decay will also play the role. So, the penetration depth of this photon through this material, right, also through this intrinsic material also influences, right. So, there are two aspects. Physically, it is one aspect is penetration depth, right, of photons physically, and the other aspect is in terms of physical electron diffusion, right, electron diffusion characteristics. Okay. So, these two characteristics decides, okay, what should be the size of this intrinsic layer, so as to allow less electron, right, diffusion and more penetration basically. Okay. And so, this aspects are important. How do we determine what is the penetration depth? As we already know in right, Beer-Lambert's law, very right. So, P transmitted output, right, output is P in into exponent of minus alpha to x, right. Alpha is nothing but absorption coefficient, okay. And let us say we are considering indium gallium arsenide, right, pin photodetector, okay, pin photodetector. Okay. So, we know alpha at, let us say, absorption coefficient alpha, you need maybe centimeter inverse or micrometer inverse, etc. Let us say for at the wavelength 1300 nanometer, which is the light source, and we want to detect this, right, intensity or the power of this light source with the help of this indium gallium arsenide pin photodetector. Then we also know the absorption coefficient by this pin photodetector for the wavelength at the wavelength 1300 nanometer is absorption coefficient alpha is approximately 1.5 micrometer inverse. Okay. What it means, the intensity of the transmitted light will decrease by 1 by E of its based on from the input intensity in the, right, when it travels photons travels by 1.5 micrometer, okay, length. So, so from this we can easily estimate basically, right, the transmitted intensity at, right, and let us say let us say if it is travelling through pin photodiode, and if the length, okay, if the length through which it is travelling is around 0.15 micrometer. Okay. So, this is basically, if I see in terms of wordings, thickness, right, of this pin layer thickness is 0.15 micrometer. So, what is possible? We can estimate Pt by Pin, which is equal to exponent of minus alpha into x, exponent of minus alpha is 1.5 micrometer inverse into, right, thickness 0.15 micrometer. So, this will be 0.8 right. That means the 20% of the photons will get absorbed, right, when it travels through the this spin photo detector whose thickness of this intrinsic layer is 0.15 micrometer, is not it. So, we will be able to estimate based on this simple approach the depth of penetration. Okay. So, still we can have a little longer length depletes, right. So, that even more absorption is possible. Okay. The more the number of photons gets absorbed, the more number of electrons will get, right, will be freed, right, dissociate. But then as you start increasing the intrinsic layer thickness to certain extent, so as to improve the absorption, you end up with a diffusion problem, because now electron which is produced will have to travel for a longer distance till it reaches the n type layer. Okay. But in meantime it may get absorbed, diffuse because of the electron interaction with the material, etc. So, basically diffusion also comes into picture, is not it. So, the diffusion length, okay. So, this is penetration, right, of photon penetration basically, right, of photon penetration, how much photons can penetrate to the material, and there is a diffusion, okay, which is right. And diffusion length ln is equal to dn tau n raised to half, okay, or for holes lp dp tau p raised to half. Okay. It is given by this form, where ln is of course diffusion lengths, okay, diffusion lengths ln and lp are the diffusion lengths for electrons and protons, sorry, holes diffusion length, right, and dn and dp are the diffusion coefficients. So, larger this diffusion coefficients, the small, right, the diffusion length will accordingly, right, will get accordingly decided. Okay. So, diffusion coefficient are there, and tau n and tau p, okay, is the diffusion lifetime. Okay. It represents lifetime. Okay. So, right, by the time it travels, it may get diffused depending upon the diffusion coefficient, diffusion length. So, this lifetime determines, right, the decay characteristics of the electron getting diffused in the layer. Okay. So, these aspects, maybe one example like the previous example if I have, no, or maybe afterwards if I no, it's not there. Of course, these are all material dependent characteristics. Okay. We will not be able to alter too much. Diffusion characteristics of different materials will be well decided, and accordingly the lifetimes are of this, right, electrons getting diffused is decided. So, which determines the diffusion length which is available, right. So, if the diffusion length is 1.5 micrometer, and if I have intrinsic layer which is 3 micrometer, I am sure that electron will not reach to, right, before it reaches to the its right p or n, right, and through this intrinsic layer it may get absorbed. Okay. Probability is very large. So, this diffusion lengths parameters are also useful based on material characteristics we can easily determine. And the next factor is optical absorption. Okay. Basically again it is based on the alpha value, correct, alpha value. However, I will try to give you, so this aspects. Okay. Here x axis is wavelength, y axis is the absorption coefficient. Now, these materials silicon, gallium arsenide, germanium, indium gallium arsenide are all arsenide phosphide are all semiconductor photodiodes. Okay. Their characteristics you can see that are different depending upon the wavelength. You can see that the absorption coefficient is decreasing as absorption coefficient decreases right up to certain wavelength, and then right falls down to right minimum. Now, so what it means? Okay. Now, let us say if I am going to a shorter wavelength measurement, right. So, if I am using let us say silicon below 400 nanometer, 0.5 micrometer is 400 nanometer wavelength. If I try to use silicon as a photo detector to detect the light of the source whose wavelength is less than 400 nanometer. Okay. In that case, the absorption coefficient is quite large. What it implies? That photon will not be able to penetrate too much into silicon, it will get absorbed in a very small thickness layer, correct, it will get absorbed. That means the the electrons which are generated etc. Will be very less, and even if they generate, they will have to travel a long distance through that detector part. Even if you try to reduce that length, you may be able to cover the diffusion length, but the limitations are absorption is quite large. Okay. So, so that is optical absorption coefficient is quite large. On the other hand, right, if I go with longer and longer wavelength where absorption is less, photons will be able to travel, but then the photon energy reduces, and if it is less than the energy band gap of the material, it will not be able to dissociate the electrons and holes into, right, pair dissociation will not be possible. So, the cutoff wavelengths are decided on either side based on the photon energy as well as the absorption, right, parameters. So, that is why you will see now from this we can easily find out what is our requirement. Let us say I want to measure wavelength optical power at a wavelength around 1.6 micrometer, then certainly silicon may not be a good, right, choice, right, because it will be only transmitting the light, absorption is very less. Over and above of those photons will not be able to dissociate this electron hole pairs in silicon. So, it is only getting transmitted, we will not be able to do any measurements. So, we will prefer in that case photo detectors based on indium gallium arsenide phosphide or indium gallium arsenide material etc. Okay. On the other hand, right, if we are using, if you want to go for a shorter wavelength, right, maybe silicon is better up to 400 nanometer. Okay. Still there are some other approaches to improve this measurement characteristics by using black silicon etc., in the sense that the surface of the silicon material will be modified, so that the number of photons which will get absorbed and produce number of right electrons will quantum efficiency can improve, then it may help us in measuring even a little shorter wavelength. I think it goes up to 180 nanometer or so measurements, okay. But below that the photo detectors will not be able to work, because most of the photo detectors will absorb the light. We need some other approaches to measure the power, right, below this etc. We will stop here today. We will continue tomorrow the class related to of course some characteristics of this photo detector, what is the meaning of quantum efficiency, and what are the other types of detectors such as of course silicon etc. can be used with CCD, with CMOS sensors, and then we will extend it to extend some other types of sensors based on photocathode, right, photocathode photons sorry electrons generated.